We've talked before about motion in a circle, where the object traveling around the circle is moving at constant speed. That type of motion actually has a special name. It's called uniform circular motion. Now in that motion, we said that the velocity was tangent to the circle, whereas the acceleration pointed in toward the center of the circle. Well, that acceleration actually has a very specific type of name as well. It's called centripetal acceleration. And the centripetal acceleration is going to depend on a few things. Suppose you're trying to run around in a circle. Okay. Running around in a circle, how much force do you have to push yourself to keep yourself moving in that circle? Well, when you're running, you're really pushing against the ground. And if you are running faster around that circle, it's going to be harder to curve. It's much harder to change directions when you're running at full speed than when you're just jogging. So the centripetal acceleration, how much acceleration you need to move in a circle, is going to depend on how fast you are moving. So it's going to depend on your speed, v. In addition, it's harder to make a tight turn than it is to make a wide turn. So if you are running around a track, the track has a pretty wide turn. It's not that hard. Maybe you lean a little bit while you're running. But if you try to make a turn in a circle that's only a few centimeters big, that's very difficult, especially if you're running at full speed. So it's going to be, you're going to have a bigger acceleration for a tighter circle, or a circle with a smaller radius. So for that reason, the acceleration, the centripetal acceleration, is also going to depend on the radius, which I will call r. Now, if I do just a little bit of dimensional analysis, we can find that our centripetal acceleration, the magnitude of our centripetal acceleration, is equal to the speed at which you are moving around that circle divided by the radius of the circle. As you go faster, you need a larger centripetal acceleration to keep yourself moving in the circle. Not only that, but as your circle gets smaller, as r gets smaller, you need to accelerate more to stay in that circle. Tight circles require a bigger acceleration than wider circles. There are some other important quantities to consider when describing uniform circular motion. One of these quantities is the period of the motion. We define the period as the time it takes to repeat the motion. So suppose you start at the top of that circle, and then you run around the circle and end up back at the top of that circle. The time it takes to go around is known as the period of the motion. So that's the time for one revolution. One revolution. There is another quantity called the frequency. Frequency, which is equal to 1 divided by the period. So we could say it takes 1/10 of a second to go around in a circle. That would be the period. 0.1 seconds, 1/10 of a second, is the time it takes per one revolution. We could also say equivalently, if it takes 1/10 of a second, then you would be going around with a frequency of 10 times per second. So 10 revolutions per second. So we can go back and forth between period and frequency interchangeably. They provide the same information. How do we find what the period of an object's motion is? Well, there's actually a very simple way to do it, because I know if my speed moving around that circle is v, and I want to find the time it takes to go around. Well, I know v is the change in distance over the change in time. And the distance that you travel going around one circle is just equal to the circumference. The circumference of a circle is 2 pi r. I'll write it this way, circumference equals 2 pi r. Therefore, the time it takes to go around that circle, let me give myself a little bit more room here. So the circumference is 2 pi r, which means the time, the period it takes to go around, is going to be the distance you travel divided by the speed. So that will just be 2 pi r divided by the speed, which was just v. So if you know your speed, you know the radius of the circle, you can figure out the period. And from the period, you can figure out the frequency. When you fire a projectile, we know that the projectile curves towards the surface of the Earth. And if I fire it a little bit faster, it still curves towards the Earth, but it goes a little bit further. The curvature is a little bit less. If I fire it even faster, again, the projectile goes a little bit further. But at a certain point, we will fire the projectile so fast that the curvature it makes is going to start to match the curvature of the Earth itself. So if you fire a projectile with enough speed, the Earth's gravity is going to accelerate it. Gravity will always pull it towards the center of the Earth. But that's exactly the type of acceleration that you would expect to have. Whereas this is just the acceleration of gravity. It's the exact same as the type of acceleration you'd expect to have for uniform circular motion. So it must be true that in the absence of air resistance, if you ran really, really fast and jumped, you could make it all the way around the Earth and just kind of keep floating a foot off the ground. Again, not a realistic situation because there's some air resistance which will eventually slow you down. But let's say you were to do this on the moon or some other planet. You should be able to run really fast and jump, and then just hover about a foot around the surface of the planet as you essentially enter what's known as orbit. So this is exactly the same type of orbit that the moon has going around the Earth. It's the same orbit that the Earth has going around the Sun, except for this example, we said it was only a foot off the ground. The moon is orbiting the Earth. It's obviously a lot further away than 1 foot off the ground. But you can, in principle, run really fast. And if there was no air friction or air resistance, you should be able to run fast enough that if you just picked your feet off the ground, you would continue to go around the Earth. How fast is that? Well, to figure that out, this is just kind of a fun problem that I like. We need to know the radius of the Earth, which I'll call our Earth, and we need to know the acceleration of gravity. Because we know that in this case, the acceleration of gravity is a form of centripetal acceleration, because it's moving in a circle. We know from before that the formula for centripetal acceleration is just v squared divided by the radius, which in this case is the radius of the Earth. Now if I solve for the radius of the Earth, if I solve for v in terms of the radius of the Earth and g, we'll figure out exactly how fast you have to run. Okay, so if you were the Flash, you should be able to do this if you run really, really quickly. Let's solve for v. I'm just going to move radius of the Earth over to the other side and take the square root. We'll get that v is equal to the square root of g times the radius of the Earth, which is equal to square root 9.8 meters per second squared times the radius of the Earth, that's 6,400 kilometers, which will give you, assuming I did my math correctly, about 7,900 meters every second, or equivalently, about 18,000 kilometers an hour. Kilometers? No, excuse me, miles per hour. So if you can run 18,000 miles per hour, you can jump and orbit a planet the size of the Earth just a foot off the ground. Again, assuming there's no air resistance.